On the recording. All right, so everyone can see my screen, right? I guess that's a yes. So, welcome. Oh shoot. All right, welcome to the Paragon X Advanced Techniques and Mechanics. Today is the second class. Today's August 1st, right? Yeah. So today's second class, we're gonna be talking dynamics. So, applying F equals ma, momentum, and also energy, right? So here's a review of our class structure. So we're gonna start by reviewing the homework. Oh yeah, we actually do have homework we have to review today. So uh, let me scribble off that part. We do have homework to review today, and remember, homework it's assigned every week. It's not mandatory, but try to look at the problems and do what you can. I recommend you guys spend like at least an hour on the homework problems. This week there are only four problems, right? And I got a lot of your homework submissions, and I really like what I saw. So keep it up. And if you didn't submit your homework, just to let you know, you can always submit it to me on Discord or email it to me, and then I'll reply. Try to reply within like a day and then give you some feedback. And this way you can improve. Okay. So, all right, class will mostly be lecturing, practice problems used to show concepts. Videos must be all on at all times. I know a lot of you guys have your videos off. I'm just gonna assume that your camera doesn't work. I'm just gonna go by an honor code system. And most important, ask questions. That's how you can get better, all right? So let's get started. Yeah, this is a review of our syllabus. So yes, last week we did statics. This week is dynamics. Next week we're gonna try to do oscillations and rotations, and then next week, which is gonna be our last class, more rotations and gravitations. And if you have not already, please join our Discord server. It's gonna be really helpful. It'll help communication between us and you, and it just helps everyone, right? Okay, let's get to some actual content for today. Homework review. All right, this is the first problem, part A, right? As an exercise, try to prove the following claim. If forces are applied to 3 points in a static system, then the extensions of the vectors representing the net force at each of the 3 points must be concurrent or parallel. All right, no, that was a mouthful, but let's first look at the picture. So say maybe we have like some system, I don't know, I'll just draw like you just have a body like that in general, right? And then you have forces applied to 3 points. So maybe you have a force over there, points that way. And then maybe I have another force that points this way, and another force that acts over here and points this way, right? All right. And let's check out the conditions the problem gives us, okay? Um, Apply to 3 points in a static system. Static system. What static system means? Static system, it just means that you have sigma F equals to 0 and sigma of the torque equals to 0. So the system is under force and torque balance. And all right, what do we want to prove? Okay, we want to prove we extend the vectors representing the net force at each of the 3 points. It must be concurrent or parallel. So, all right, I want to emphasize something here is that we're looking at the vectors that represent net force at each of the points. Um, so what does that mean, right? So some of you guys ask me that like, okay, what if you have a system and you have forces applied to 3 points in the system, but maybe you have like five forces in total. You don't have three forces. Well, that's no problem. So for example, if I also have a maybe instead of having one force over there, I'll have two forces. One points in this direction and one points in that direction. Does that mean that we can't apply whatever theorem we're like this theorem we're trying to prove? Well, no, that's not true because just because you have two forces that are applied at one point doesn't mean that you can't replace it with just a single vector representing the net force there. So instead of drawing those two vectors, I can replace it with a single net force vector, which let me draw in red. Oh, it's gonna look something like oh give me a second. All right. It'll look something like that, right? That's going to be net force at that point. and um, I'll replace the other two drawings I made, other two forces I drew, right? And so just because we have, for example, 5 or 6 forces applied at a system, as long as there are only a total of 3 points at which the forces are applied, we can still apply this theorem that we're trying to prove. Okay, just wanted to make that clear. So, okay, let's just say these three vectors I drew here, they just represent the net force at these 3 points. And just to make it look nicer, I'll replace that red one with the green with the green vector. Okay, so looks something like this. All right, what were we trying to prove? The extensions of the vectors representing the net force at each of the 3 points must be concurrent or parallel. So let me draw the extensions. Say extends that one looks something like that. That one will go there. That will go there. Okay. It's not a perfect drawing, but you guys get what I mean, right? And then they all intersect at this one point over here. Yeah, so they're concurrent, right? Well, we'll first deal with the concurrent case, right? So we're given our condition that we're given is that we have the sum of the forces 0 and the sum of the torques is 0. Okay. And then we're also given that yeah, so we want to prove that the extensions of the vectors representing net force, yeah, they must be concurrent at this point over here. And then, so how do we prove this? Well, let's go back to our definition of torque, right? What's the definition of torque? Remember, we said that we said torque equals to F cross R, right? Force vector cross the radius vector. Torque will also be a vector, right? Now, in this case, if you have the net force vectors, their extensions are parallel to the radius vector, right? Because they all meet at the same point. If you're taking torque about this yellow point over here, then you have F is being parallel to R, right? What does that mean? Then that means the torque produced by each force is equal to 0. And so sigma torque is equal to 0. And now, okay, we found that the torque about this one point is equal to 0. How can we show that the torque about any other point is 0? Well, remember last class, we proved a theorem that said basically, if you know that you have force balance and the torque about one single point is 0, then we can show that the torque about any point is 0. So in other words, we have a static system here, and we basically just proved it here because we showed that if the forces, the extensions of the net force vectors, they're concurrent, then that means that the radius vector is always parallel to the force vector, meaning that your torque would always equal to 0. And because your net force is equal to 0, then you know that the torque, the net torque about any single point in space, it will be equal to 0. So you always have sum of force is 0, sum of torque is 0. So we just proved that, yeah, we basically proved the theorem. So if you want to apply this, right? For example, you're given that a system is static, right? Then basically another way to solve the problem, which will involve geometry instead of writing like your torque balance or force balance equations, it'll be more focused towards geometry. And then how it'll work is that if you know that there are forces at 3 points, then you just want to find the condition for the net force vectors to be concurrent. Okay, does that make sense? Or any questions? I welcome them, and please type them in chat or just interrupt me and ask me the question. Okay. All right. I'll just keep going. So right there we showed that uh they can be concurrent, right? Now, what about the case where it's parallel? Well, um, so parallel, right? That's just another way of saying they're concurrent at infinity. So basically, in other words, concurrent is sort of encompasses the parallel case. So we can just say that if the forces are applied to 3 points in static system, then yes, indeed, we have just proved that if you extend the net force vectors, they must be concurrent or parallel. Okay. Now let's go on. By the way, any questions about that? I guess it seems good. So let's go on. So part B, right? If we have forces acting on more than 3 points in a static system, must the extensions of the net force vectors at each of the points be concurrent or parallel? If your answer is no, give a counter example. Um, let's see. Let me call on someone here to give me their opinion. Um, Sing, do you have any opinion? Do you think this is true or this is not true for part B? All right, I guess maybe microphone's not working. So uh Avi, you am I saying your name correctly? Do you want to give us your answer for part B?
I think no, but I don't actually have any like good proof behind it.
Yeah,
Just
don't worry. No is the correct answer. And I'll give a counter example here so that you guys can see it. So I'll erase some stuff here to give some space. So for example, let's take the case where we have forces acting on 4 points, right? So if we have forces acting on 4 points, let's say, for example, let's say you have a rod here, right? Just a regular rod, and then maybe we're applying forces at 4 points on the rod, right? For example, we apply it on maybe we'll apply one force this way at the end, another force this way at the other end, right? And then maybe their extensions, they'll go, if I extend them, they'll meet somewhere there at that point over there, right? Now, maybe I have let's say I've got two forces over here. I'll draw them because I'm running out of space. So maybe something like that. There's one force there. There's another force that way. And then if I draw their extensions, they'll extend and then they'll meet at a point over there, right? Now, first, okay, here in this case, we have four forces and they're not all concurrent, right? Because we have two intersecting at one point and the other two are intersecting at a different point, right? So we don't have all four force vectors meeting at the same point. Now let's just double check if we can have force balance under this case. And the answer is yes. So force balance, if we look at the horizontal direction, right? Uh, like there will be a component this way, a component this way for that force, and there's also a component this way and a component that way, right? So those two horizontal components, they'll cancel out if those two are symmetrical, right? We'll just say they are, but yeah, they're going to be symmetrical and then they cancel out. And then what about these vertical forces over here? How are they going to get a balance? Well, if we decompose the green force vectors, so we decompose them like that, then first, for the green force vectors, we do have the horizontal components, they cancel, right? Because they're in opposite directions and equal magnitude. Now, we're going to always be able to adjust the angle or the magnitude of the green force vector such that the sum of those two will always be equal and opposite to the sum of those two. So in other words, in this case, let me undo everything so you can see the counter example better. Right, in this case, we have four forces. We have force balance. We also have torque balance, but the extensions of the net force vectors, they're not concurrent. Two of them are concurrent and the other two are concurrent, but they're not all four simultaneously concurrent, which means that this theorem does not apply when we have forces acting on more than 3 points. So the answer is no. No is the answer to part B. Uh, does that counter example make sense? All right. I
Sorry,
was sorry. Yeah.
you asked you asked to me before,
Sorry.
and you talked to me before.
Um. No. I don't think. No, I don't think so.
Okay, okay.
Okay. All right. So yeah, for part B, the answer is no, and this will be our kind of example for it. All right. Um, yeah, go on to the next problem. All right. Recall the following problem which we solved by writing force and torque balance equations. Yeah, this one we solved last in class. But we want to solve it using the idea we just proved, right? So ladder leans against a frictionless wall. The coefficient of friction with the ground is mu. What's the smallest angle the ladder can make with the ground and not slip? We want to use what we proved in part A to solve this problem without having to explicitly write out any torque balance equations. All right. So let's just make a drawing here. We have this will be our wall, and this is our ladder, right? And it makes an angle of theta. And then let's draw our forces again. I'm pretty sure everyone knows how to do this, so I won't call anyone for this for the sake of time. That's the gravity force. Let's say this is normal force 1, and we'll also have a normal force 2, right? And 2, and then the friction force, right? Because the ladder wants to slip down, we'll have the friction force pointing this way, where F1, right? And F1, it will take on the maximum amount of friction when your theta is at the minimum, because that's when the ladder wants to slip the most, right? So, right, we don't want to write out any torque balance equations, but first let's do some force balancing, right? So, of course, if we do vertical force balance, then this N1 over here, we can replace it with gravity, right? Because it's the magnitude is equal to gravitational force. Oh shoot. Because we need to have vertical force balance. Then because F1 is, as we know, F1 is the friction coefficient times the normal force, then I can erase the friction force. I'll replace it with mu mg. And now I want to replace N2 with mu mg, right? Because we have horizontal force balance. So mu mg over here, right? Now, I want to, because it's a static situation and I have forces applied to 3 points on the system, then that means they have to all intersect at a single point, the extensions, right? They intersect at a single point. So if I draw all the extensions here, so of course, gravity and the normal force at the top, right? They'll intersect over there. So I want the angle such that it intersects the extension of the net force vector over here, it intersects at that point there, right? And how would I do that? Well, I know that for example, let's say this angle over here, right? So I'll draw a right triangle here. That angle, let me call it beta, right? What do we know about beta? Well, I know that tangent of beta, that's equal to 1 over mu, right? Because because it's just going to be the net force over here. So I'm just adding the vertical mg force and the horizontal mu mg force, right? And then I want tan beta, right? Tan beta is 1 over mu, but it's also going to be equal to if I divide this length by this length, right? And what is that? It should also equal to, because the ladder has full length L, right? So this will be L times sine theta. So L times sine theta divided by this length over here, that's half of L cosine theta, right? So L over 2 cosine theta. So I have, if those two cancel, and this goes up to the top, right? So we have 1 over 2 mu equals to tan theta, which is the same conclusion that we got during class last time when we used force and torque balance. But this time, notice how we applied the theorem that we proved in part 1a, right? So we proved that the extensions of the net force vectors, they had to be concurrent. And we're getting the same answer here, which is good, because it means it works, right? Any questions about that? Hopefully that was a straightforward application for you guys. So let's go on then. Yeah, there doesn't seem to be anything, so all right. Homework number 1. Uh, think I think how about this? So because this will take a bit of time, how about for the sake of time, I'll go on to the next homework problem because this one is pretty similar to the last one. If you guys are really curious, I'll attach the solution to this problem in the next email. So in 1 or 2 days, I'll write up the solution for this. But because today's gonna be a pretty heavy lesson, I'll just skip over this problem for now. We can go over the other homework problems. Is that okay? Okay. Yeah, if we have time at the end of class, we can go back to that problem and go over it, but I'll definitely attach a solution for you guys. So just in case you still want to know how to solve the previous problem. So let's look at this problem, all right? Rope between inclines. Rope rests on two platforms that are both inclined and angle theta, which are free to pick. The rope has uniform mass density, and the coefficient of friction between it and the platforms is 1. The system has left-right symmetry. What is the largest possible fraction of the rope that does not touch the platforms when angle theta allows its maximum fraction? Okay, so how about let me draw a bit bigger for you guys. It will be easier to see. So it looks something like this. A rope. That will be our rope, right? All right. And then this is an angle, this will be theta. It's also theta, right? And then fraction of the rope that's not touched the platform. So let the fraction be, say we have a fraction f, right? And then, all right, so the big idea for solving this problem is you want to divide it into many systems, right? Because we're looking at, it's like part of the rope, it's like not on the platform, and part of the rope on the platform. So if we first take a look at the system where we have, it's just the rope, part of the rope that's not on the platform. So let's box it over here. All right. That system, what will the forces be on it? Well, we'll have a downward gravity force, which will be Fmg, right? It's only part of the entire rope, so it experiences only part of the entire gravitational force. And the other two forces on it is just tension, right? Tension, tension. And they're angled at a, they have an angle theta with the horizontal, right? So if I want to balance forces here, then it's just because the horizontal components of tension cancel, right? So the force balance equation will just be 2t sine theta. It equals to 2t sine theta, theta equals fmg, right? And then now if we want to consider a different system, right? If we want to consider system on the side here, then let me draw it on the side. So if we're looking at the slanted part of the rope that's on the platform, then what will the forces be on it, right? So there'll be a force, tension force that way. There's a gravity force with the magnitude of 1 minus F over 2 times mg, right? Because it's, again, it's only part of the rope, but now it's the part of the rope that's on the platform. And then we got a normal force. And then, of course, for there to be force balance, right, has to be a friction force to the right. And then yeah, so we want to, yeah, we want to maximize the fraction on the, oh shoot. Yeah, we want to maximize the fraction of the rope that's not on the platform. And for naming purposes, let me not call that F. I'll call the friction force FF. Do not confuse it with the fraction, okay? So if I want to do force balance here, then what will be our equation, right? So normal force N equals to 1 minus F over 2 times mg cosine theta. And then if I want to balance forces in the other direction, in the perpendicular direction, then what will it be? Well, it'll just be T plus 1 minus F over 2 mg sine theta equals to FF, right? When what is FF? It's mu times N. So it will be 1 minus F over 2 times mu mg cosine theta, right? And then, oh wait, t over here, right? I can solve for t over here. How do I solve for t? Well, t would equal to fmg over 2 sine theta. So if I write everything on the right over here, okay, just to keep it neat, I'll change the color too. All right, so then notice we can cancel mg, right? Mg, and then we'll divide by mg here, divide by mg. So what we get, yeah, it should be f over 2 sine theta Yeah, and then plus 1 minus f over 2, 1 minus f over 2 sine theta, right? And then that equals to 1 minus f over 2. And then we know we're given the coefficient of friction is 1. So mu is just equal to 1. So it's just 1 minus f over 2 cosine theta. And then I want to isolate f, right? So how do I isolate f? Oh, by the way, I can cancel the 2 here too. So f, that'll be f times 1 over sine theta, and then plus cosine theta minus sine theta. What is that equal to? It should equal to, so I'm moving everything to the right side now. So it equals to cosine theta minus sine theta. Now, how do I simplify, let me switch color. I want to simplify this over here, right? How would I simplify that? Well, what's 1 over sine theta minus sine theta, right? So we're running a bit out of space here, so let me clear up some space here first. Erase this part. All right. So 1 over sine theta minus sine theta, right? Oh. Now, 1 over sine theta minus sine theta, we work it out, it's cosine squared over sine theta, right? Cosine squared theta over sine theta. So that means that f, let me divide this so that makes more sense. So f equals to cosine theta minus sine theta over cosine theta minus cosine squared theta over sine theta. And if you look at it again, I can take out a cosine theta over sine theta in the denominator and type this equals to tan theta and then times cosine theta. So cosine theta minus sine theta. That's getting a bit messy. So okay, okay. And then I'm multiplying by sine or cosine in the bottom, right? So what? I think this in the top there should be. Ooh. Anyways, yeah, I think. Give me a second, guys. But yeah, it should be divided by. This should. Oh yeah, plus. It's a plus over here, so it's divided by cosine theta plus sine theta, right? Yeah. And then basically we want to maximize f over here. So how did you do that? Well, basically you just say we'll set df over d theta to be equal to 0, right? Once you set df over d theta to be equal to 0, you'll get theta equals to pi over 8, eventually once you solve it, right? And then you'll find that f equals to 3 minus 2 square root of 2, and that should be around like 0.17, okay? So make sure you got the answer. Um, at the end, once you understand everything conceptually, it's just a matter of doing the algebra and like taking the derivative. But other than that, it's a pretty good problem. So that should be your final answer. So theta equals pi over 8, and fraction is 3 minus 2 square root of 2. Any questions about that? So I know that was like kind of long, but main takeaway from the problem is just that you want to, like, when you're dealing with this rope system, you want to divide it into 3 separate systems. So one system will be like the part of the rope that's not touching the platform, and then there will be 2 other systems, which will be the parts of the rope on the left and the right that are not touching, sorry, that are touching the platforms. you want to analyze the forces on all three of those systems, and then you can set like force to be equal to 0, right? We don't need to consider torques here. It's just force balance here and working out the algebra. Does that make sense to everyone?
M is the mass of what?
Sorry, N?
What is M?
Oh, yeah, N is the normal force from it's the normal force from the platform on the section the
M,
rope of the platform. You're talking about,
M, the M
oh, M is equal to the mass of it's the mass of the entire rope.
of the entire rope.
Yeah, of the entire rope.
So F is the fraction of the rope.
Yeah, F is a fraction of the rope that is not on the platform. Yeah, sorry, I didn't make that clear.
Okay, thank you.
Yeah, sure. I like that question. Yeah, let's keep going. We're 30 minutes in, so oh shoot. Yeah, so let's go on to problem 9, homework problem number 3. All right. A plate bent at right angles along its center line is placed on a horizontal plate cylinder of radius r as shown. How large does the coefficient of static friction between the cylinder and the plate need to be if the plate is not to slip off the cylinder? All right. So first, of course, let's write all the forces. So let's say the plate, it has mass. For example, for convenience, you'll see why I do this, right? Let's say it has mass of 2m. What's this mean? If I divide it into 2, right? I'll divide it into a piece over there and a piece over there. What does that mean? Then that means that oh, I'll have a gravity force downwards, mg, right? There'll be some normal force, let's say n1, right? And there'll also be a normal force downward. Let's say n2. There's going to be a gravity force downwards, right? mg. And then there will also be some friction forces, right? So what direction will the friction force be? There will be, yeah, so because we have a normal force over here that points to the right, then there needs to be something that balances the force to the right, right? So we need a friction force that points to the left. That'll be F1, right? And it makes sense because you know that the plate, it kind of want to slip that way, right? It's going to slip that way. And that'll also help us say that the friction force on the bottom part of the plate, F2, it will point in that direction. So that'll be F2. Okay, now we want to basically just set all the forces and torques to be equal to 0 on the system, right? Let's do some force balance, right? In the horizontal direction, there are only 2 forces, right? There's F1 and there's N2, all right? So first of all, F1, right? What is that equal to? F1 equals to mu1 N1, right? So let me first replace that on our diagram. Instead of writing F1, I'll write mu1 N1, right? So I have mu1 N1 equals to N2, right? So I'm basically, you guys don't see, I'm looking at this force over here and this force over here. They have to balance for the system to be static. So N2 equals to mu1 N1. So N2 equals to mu1 N1. So let me replace N2 over here. I'll write instead mu1 N1. Now, okay, what does this mean about F2? Because we know that F2, oh, sorry, F2 equals to mu2 N2. By the way, you might be wondering, why am I using mu1 and mu2? Well, the reason is that we're saying that the cylinder plus the plate, right? They're supposed to be static. So in static situations, your friction coefficient, your static friction coefficient, right, is fixed, but the friction force, the static friction force, let's say Fs, is always less than or equal to the static friction coefficient times the normal force. So I'm not exactly sure yet whether whether I have the same mu over here and over there. So like I don't know whether the coefficient of friction at the top part on the top part of the plate and on the bottom part of the plate, whether they'll take on the same value. We don't know that for sure. We need to make sure whether that's true, right? So I'm just being I'm being safe and I'm using mu1 and mu2, okay? We'll eventually see that they're equal, but this is always a good practice just to make sure when you're dealing with static situations, okay? So because F2 equals mu2 N2, and I know mu2 is mu1 N1, and this just equals to mu1, mu2, N1, right? Because we just put that in there, right? Okay, and then so let me replace F2 then. F2, instead of writing F2, I'll write, let me draw in blue so that it will be easier to see. So mu1, mu2, N1. Okay, now let's just balance some torque, right? So let's balance torque about this corner point over here. So let me draw that yellow. All right, let's balance.
Hello.
Yeah, what's up?
Um, so when not slipping, can it also not like move the cylinder
Oh
or
yeah,
something?
that's a great observation you're making. Yeah, I really like the comment. I also was thinking about that too, because basically what Sui is saying is that you have the friction force on the plate. It's pointing one of them is pointing towards left over here, right? Another is pointing to upwards over there. And if I'm looking at the reaction force on the cylinder, then there'll be one pointing this way and one pointing that way. And we're asking, won't this cause the cylinder to move? And that's a great question. So basically, what the problem didn't say is that we're fixing the cylinder. Oh wait, yeah, they did say it. So it's a horizontal fixed cylinder. So even though these friction forces, they are causing a torque on the cylinder, right? Except we're assuming that there's like some sort of glue or like there's someone that's making sure that the cylinder doesn't move. So yeah, basically we're just assuming that we're fixing the cylinder even though you had like friction forces creating a torque on the cylinder. Does that make sense? So basically there will always be some sort of
Yeah,
yeah.
I didn't catch the
No, it's okay.
fixed part. Yes.
No, but yeah, that's a great observation you make that like it'll create a torque. It causes the cylinder or like it'll create a torque on the cylinder, right? Uh, but except like we know that it's just like we're saying the cylinder is fixed. But yeah, it's a great observation you make. Yeah, does that make sense to everyone? All right, so oh wait, let me check. There's a question in the chat. Oh yeah, this the weight of each portion rests in the middle of each because yeah, we can draw the gravity force on each portion to be at the center of like each part of the plate because we're assuming that the plate has uniform density as usual. So yeah, we can just draw at the plate. Yeah, good question. So let's balance torques now, right? What are the forces that are creating a torque? Well, we first have this normal force, we have this gravity force over there, and then, oh, I think it's got a bit erased, but we have the normal force over there that's causing a torque. So the gravitational force and the normal force on the bottom part of the plate, they produce a torque in the same direction. So we have, so mg r over 2 plus the mu1. Oh shoot, sorry. Yeah. Yeah, we can write yeah, this is torque balance. We also have to do a force balance, right? So let's first write torque balance mu1 n1 r over 2. This equals to what is it equal to? It has to equal to n1 times oh shoot, there's no over 2, my bad. There's no r over 2, so it's just n1r, right? But of course this r just cancels, right? So um yeah, the R cancels. So there's no R. It's just mg plus mu1 n1 equals n1, right? Or mg plus mu1 n1 equals to n1. Yeah, I think that's correct. If we want to do force balance in the vertical direction, right? Yeah, this is right. Yeah. So 2 mg, this is vertical direction force balance, by the way. So 2 mg, what does that equal to? That equals to n1, this force plus this force, but I can factor out the n1, so it's n1 times 1 plus mu1 mu2. So first, this means n1 equals to 2.
Wait, why mu1 on the torque balance? Is it not just n1 and n2?
Oh yeah, but we found that n2 equals to mu1 n1, remember? We're like,
Oh,
yeah.
okay,
Because
yeah.
it's horizontal force balance, right? So friction force is equal,
Mhm.
yeah, top friction force
Yeah.
equals to bottom normal force. Yeah, good question. So n1 equals to 2 mg over 1 plus mu1 mu2. And now we can plug that, we can plug that in here,
Why does
right?
N1 cause torque? Because
Huh?
it's pointed.
Sorry?
Why does N1 cause torque? Because it's parallel to the radius.
Oh, yeah, so right now we're looking at torque about, sorry, I didn't make it clear. So we're looking at torque about the point in the corner.
Oh,
Yeah, we're looking at torque about point in that corner. Yeah, if you're looking at torque about some, like for example, the center of the center of the cylinder, then yeah, it does, N1 doesn't create a torque. But right now, for convenience, we're looking at torque at the corner of the plate, right? We could also do torque balance about the center of the cylinder. In that case, N1, yeah, it doesn't make any torque, but there will be other forces creating torque, right? But yeah, good observation. So yeah, this will be what we're getting from torque balance. Sorry, this is what we're getting from force balance. Plug it into the torque balance equation, then that means, what does it mean? Okay, it means mg equals to n1 times 1 minus mu1, right? And then n1 we know is this. So first off, because there's an mg and n1 and also an mg over here, I'll cancel that out. And what we should be getting would be 1 equals to 2, 1 minus mu1, and then divided by 1 plus mu1, mu2, right? And then we do some algebra, right? Multiply it to the left side, subtract the 1 over. You guys should know how to do this. So it will be mu1 times 2 mu1 plus, yeah, I think this is correct. Oh, wait, I don't think there's a mu1 over there. So 2 plus mu2, this should equal to 1, right? Oh shoot, we're running out of space. So I will erase the green stuff over here, and then I'll rewrite the red stuff, okay? Give me a second. Oh, how do I erase on this? Right, that should be good enough. What do we get? Right, we got mu1 times 2 plus mu2, that equals to 1. Yeah, looks correct to me. But I erase this stuff so that, yeah. All right, so this is the conclusion we're getting. Mu1 times 2 plus mu2 equals to 1. And then right now is when we decide what's mu1 and mu2, right? So you might think that we have one equation, right? But we have two variables to solve for, right? We have mu1 and mu2. How do we solve for both mu1 and mu2 if we don't have two equations? We only have one. But the thing is, our goal in this problem is to how large does the coefficient of static friction need to be if the plate was not to slip at the cylinder? So in other words, we're trying to minimize the coefficient of static friction, right? Now, if, for example, if we have mu1 is greater than mu2, then what does that mean? That means that our coefficient of friction has to be mu1 because your coefficient of friction can't be mu2, and then you have like friction force that has a coefficient of friction that's higher than mu2, right? Your coefficient of friction in this case has to be at least mu1. The thing is, we're trying to minimize the coefficient of static friction, and because from this equation we're saying that if we increase mu1, we'll decrease mu2, and vice versa, right? If we decrease mu1, we'll increase mu2. So if we want to minimize the coefficient of static friction, what it has to be is that we need to have mu1 equals to mu2. And let's just call it mu. Does that make sense? That's a bit hard to understand, but in essence, it's just you want to minimize the coefficient of friction, and that'll happen when when both mu1 and mu2 are equal. Okay? So let's call that coefficient of friction the mu, and then we'll just have will just be 2 mu plus mu squared equals to 1. And then I'll say that for example, like that'll just be mu squared plus 2 mu plus 1 that equals to 2, meaning that mu plus 1 squared, because it's a square, right? You complete the square, right? That's what it's called. So it's equal to 2, and you're getting mu equals to square root of 2 minus 1, which is our final answer for the minimum coefficient, right? Does that make sense to everyone? All right, yeah. So it's around 0.4, which makes sense, right? So basically, takeaway from this problem, right? Draw out all your forces. Draw all your forces. Make sure you do force balance and torque balance. When you're doing force balance, do it in the horizontal and vertical direction. Torque balance, you can do it about any point, right? You can do it about the corner point of the plate. You can also do it about the center of the cylinder. Any point works. As long as you're setting the net torque to equal to 0, then you're good. All right. All right, let's keep going. Because
Wait, I have one question.
yeah, what's up?
So you analyze both parts of the plate using the same point of torque, right?
Yeah.
So is that something you have to do when analyzing two different parts of one thing, or can you create like two different points of torque balance?
Oh, good question. So if we're trying to basically like, okay, I get what you're saying. So right now, what I'm doing is, yeah, I'm separating the plate into two parts, but my system is still the entire plate itself, right? Because I'm saying that the entire plate is static. It's under force and torque balance. So if I'm trying to balance force, or if I'm trying to do torque balance on one single system, I have to choose a single point that I'm measuring the torque about if I'm just looking at that one system, right? I have to use the same point of torque, or like I have to look at the torque about one single point for every force that I'm looking at. So yeah, even though I'm dividing the plate into two, I'm still looking at the plate as a whole system. So I have to use one single point to calculate the torque about. Does that make sense?
Yeah, that makes sense.
Yeah. All right. Yeah, good question. Uh, anyways, yeah, answer equals square root of 2. You got that answer in your homework, so that's a good thing. All right, let's go on to number 10. Or no, sorry, slide 10. Homework 12-4. Two identical bricks of mass M are attached to two pulleys and placed on an inclined plane, as shown in the figure below. The pulleys are connected to a massive wall. If the coefficients of static friction between the brick and the ramp and between the bricks is mu1 or are mu1 and mu2 respectively, determine the angle theta for which the bricks begin to slip if theta is gradually increased from 0. Now this one was a tricky one, and it kind of got you guys a bit, all right? So there are a few tricky points you guys gotta watch out for. Yeah, let's solve this problem. So we're looking at two bricks here, right? First things first, we want to draw all the forces. So on the top block, right? There'll be a gravity force, let's say mg. I'll draw it here, mg. And then you got your normal force called n. We're saying between, let's call it n2, right? Because it's the top block. And then we have a tension force from the pulley that's pointing that way, tension, right? Now the question is, what direction should our static friction force point, right? Now remember, we're trying to maximize theta here, right? Or yeah, we're trying to determine, or sorry, yeah, we're determining the angle theta for which the bricks begin to slip. So basically, we want to find like when it will start slipping, right? So, like what happens is that the friction force will always try, the static friction force will always try to make the block a static, like the block under static equilibrium, right? And then as theta increases, right, there'll be more and more torque created, or sorry, mg is there's a component that points down the ramp, right? So if we keep increasing theta and we want to find the maximum theta for which it will stay under static equilibrium, then we want the static friction force between the two blocks to point up the ramp, right? Because that means we can make a theta as large as possible before it starts slipping, right? So let me call that, say F2. I know it's a bit far, so we'll call that one F2 over there, right? Now let's look at the forces on the bottom block. Maybe I'll draw it in blue so that you guys can see it better. But there will be a gravity force downwards, mg. Of course, there's a normal force, call that normal force. Now, F2, there's F2 is the force pair, right? So it's the static friction force between the top block and the bottom block, right? If it points up the ramp on the top block, it should point down the ramp on the bottom block. So I'll draw it that way, F2. Now, the next point is something, oh, sorry. Yeah, the direction of the other friction force, so the friction force between the bottom block and the ramp is something that both of you guys got, like, we're a bit confused on, right? How do we get that? Well, so F2 on the top block, F2 points up the ramp. So if F2 points up the ramp, that means the top block wants to slip down the ramp. Because remember, the friction force always points in a direction opposite to the relative motion, right? So if F2 points up the ramp, then top block wants to slide down the ramp. If the top block wants to slide down the ramp, because we have a pulley over here, that means that the bottom block wants to slide up the ramp. So if the bottom block wants to slide up the ramp, then the friction force between the bottom block and the ramp must point down the ramp because the bottom block wants to slip up the ramp. So what does this mean? This means that we have the F1, which I'll say is the friction force between the bottom block and the ramp. It points down the ramp, right? So that makes F1. It's a line of reasoning that you need to really master because if you don't get it correct, you're gonna get the wrong answer, okay? But anyways, yeah, so let's just write out some force balance equations. Oh wait, yeah, something I missed. There's also a tension force, right? So 2T to the right, because yeah, because there are two parts of the string that are pulling the pulley upwards, so we have twice the tension force on the bottom block. All right.
Can you repeat the friction explanation?
Yeah, sure. So the friction force between the top block and the bottom block, right? That points up the ramp, meaning that the top block wants to slide down the ramp relative to the bottom block. If the top block wants to slide down the ramp, because the pulley is, oh wait, so notice that we have a pulley here, right? And the pulley is designed such a way that if the top block slides down the ramp, that means that the bottom block must slide up the ramp, okay? If the bottom block slides up the ramp, then the friction force between the bottom block and the ramp must must point downwards because the bottom block wants to slide up the ramp. So the friction force with the ground or with the ramp would point down the ramp, correct? Does that make sense to you?
Well, what I'm not getting is I was thinking that the system would slip if the bottom block goes down and the top block goes up.
Yeah.
That's like how it would
Yeah. You
move.
have it correct. So the top block wants to slide down the ramp and the bottom block wants to slide up the ramp, right? So
No, I
if,
meant the other way.
oh,
I thought the bottom block would try to slide down and the top block would try to go back up to compensate.
yeah, that's what happens. So the top block wants to slide down the ramp, the bottom block wants to slide up the ramp, correct?
No, I was saying it the other way.
Oh, the other way, top block wants
No,
to,
the bottom. Oh, did you say the bottom slides down?
no, the bottom side's up.
Yeah, I was thinking the bottom slides down and the top block has to go up because how would the top block go down?
Oh, good question. So, yeah, so let's look at the top block, okay? So this is the top block. How about let me draw a magnified picture, all right? So you have the ramp over here. You have your two blocks, right? You have your top block and your bottom block, okay? And then the top block, you have a gravity force downwards, you have the normal force, right? And you also have a tension force that points to the right. And if we decide the direction of the static frictional force between the top and the bottom block, we're essentially deciding which way the bottom block slides, right? Because if we know which direction the friction force is, then the opposite direction will be the direction the motion is, correct? Because frictional force is in the opposite direction of motion, right? All right, I'll assume that's it, okay? Like,
Sorry. My reasoning was that the string is like the length of the string is constant, so it can't like move unless the bottom block moved in some way like down, because the length is or the string is connected to the wall that connects to the top block, right? So it
yeah.
can't really stretch by moving down unless the bottom block moved down
Oh,
or
okay. So yeah, I see what you're trying to say here, but look, so let me draw the pulley in our diagram too, okay? So we have this is our pulley wheel, and then this is another pulley wheel, and then we have a string attached there and a string attached there, right? It is actually possible for the top block to go up the ramp. The reason is because if the top block goes up the ramp, right? So this length over here, this would shorten, right? Which means more string goes over here. If more string goes over there, what that means is, you see this pulley wheel over here, right? This one over here, that one can move up and down. This one over here, it's not attached to wall. The top one over here, that is attached, that pulley wheel is attached to wall, but this one over here is not attached to wall. If more string comes this way, then what that means is that this pulley wheel over here, it will go downwards, meaning that when the top block goes upwards, the bottom block goes downwards. Do you see it now?
yeah, I thought that what I was saying was the bottom block goes down and the top block goes up.
Oh yeah, that's also what I'm saying.
Oh, okay.
Oh,
Yeah.
sorry. Wait, yeah. Oh yeah, that is possible. No, sorry, I'm saying that the top block is going down. Wait, you're saying top block is going up or down?
I'm saying since the top block string is connected to the wall, it
Oh,
can't go down unless the string stretches, so the bottom block has to go down so that the string goes up.
no. So if the top block is going down, that's possible. Because look, if the top block is going down, the string's not stretching. What's happening is that there's just more string from this side that goes over here. And if string, so basically we're trying to lengthen the string over here. So there needs to be string that comes from this side of the pulley to the left side, right? And how does that happen? That happens if the pulley wheel over here, if this pulley wheel over there moves upwards, then there's going to be more string coming this way, right? So the top block can move down. That is possible. You see it now?
I can, yeah, I see it, but wouldn't the bottom block try to go down? Like, wouldn't it come in reverse? Wouldn't it try to come down the bottom block because of gravity, and the top block would try and go up?
Well, yeah, there is on the bottom block, right? There's a gravitational force down, right? And there's some other forces, but remember, there's also a tension force to the right. So pulley itself, the pulley string, it's pulling it to the right. So it's possible for the bottom block to move up the ramp.
Was it because of the extra friction or something?
No, so
Or
plus we have a pulley over here, and there's a string. How about let's draw if it was vertical, right? Uh, if it's like this, right? You have a pulley. This is your pulley, right? And then that's attached to the wall. This is also attached to the wall. You have a string over here. You have a mass over here, right? Also have a mass over
yeah,
here. This string, I'll highlight in red. This string, that string has tension. That string is gonna pull this block upwards. because the reason why is that if I box
Y-
this, if I look at the forces on the wheel, right? The force,
Yeah, this one makes sense.
yeah,
That
yeah.
makes sense.
Now if you just tilt it, right? Just tilt it to the right, then we still have the same thing. There's still going to be a tension force on this red string over here, which I'll highlight over here. That one's also red, right? It's going to be pulling it to the right, upwards, right? Up the red.
Wait, hang on, wait. I'm still saying the same thing on this one. I didn't understand this one either. Like, I'm still having the same problem that the block can't go down because it's attached to the wall. So uh, that's what I'm.
Yeah, okay. So this part of the string, it is attached to the wall, but if your pulley wheel is also moving upwards, and the part of the string on this side will shorten, and there'll be more string that comes to this side. Okay? If the string, wait, if the string over here on like, how about I'll erase it?
Yeah, but how would how would it, like magically move up? Is my question.
Okay, so yeah, so if these over here, right? Thing I circled in blue, or yellow, right? This thing over here, that wheel over there, that can move up or down. That's free to move, right? So
Yeah,
so what it does, if this wheel moves upwards, then there's gonna be more string that comes to that side over there, the top side, and there'll be less string on the bottom side. This,
yeah, I agree. I agree with that. But just like my logic is, I'm thinking it would move down, not up. That pulley. I don't understand like what makes it go up.
what makes the block go up?
Yeah, is there some force that just like pushes it up or?
Uh, there's a tension force in. Remember, if let's go back to this vertical case over here. This string over here, it has tension. You see the one I'm highlighting in yellow right now, right? That one
Yeah,
string has tension. It's gonna pull up the block with like a tension force, right? Will be.
yeah,
That's the same thing over here. I have, if I'm, for example, let me use maybe, I'll use black, okay? If I'm boxing the pulley wheel, like let's treat the pulley wheel as my system, right? Then the pulley wheel, it experiences tension force, right? Two tension forces, and there's a string attached to the bottom, meaning that this string on the bottom, it has to have a tension of two times T, right? If that
huh?
string that connects to the block has a tension of 2T, that means it pulls on the block up the ramp with a force of 2T, correct?
Yeah. Okay. What about with the gravitational force also?
Yeah. So the gravitational force, there's a component that does point down the ramp. But remember, we want to look at the net force. You can have twice of the tension to be greater than like mg sine theta, right? As long as the net force on the bottom block points up the ramp, it will slide up the ramp, right?
Yeah.
Yeah. So
Yeah. That makes sense. Yeah. I don't know. Just
no, it's
like
okay.
to me,
I like your question. Yeah.
it just feels like it would move down like a regular incline.
Mm,
Like it would try to move down. It's just
yeah. Yeah, so yeah, if you just have a block on an incline, then yeah, it would move down. The thing is here we also have a string that's pulling it up the ramp.
okay. Yeah.
It's possible for the net force to be up the ramp. Yeah. But
Yeah. Yeah. Okay. I see.
why do you question me about? Yeah. Yeah, let's go on to solve the problem. We're pretty low on time, but that's all right. Okay. If we go into these things, it's good because you guys can learn more into it, right? So, um, all right. So, um, oh, true. Wait, so let's go back to doing our force balance. So I'll redo it so that it looks a bit better. It's easier to see. All right, just to review. All right, we have what are our forces? Our forces will be gravity force, mg, normal force, n, and then tension force to the right. And then as we said, we'll have a friction force that points up the ramp, F1, right? on the bottom block, it's an mg, and we have another normal force, and then we'll have the friction force, that's the reaction force, so F2 to N2, right? F2, and we'll also have the friction force on the ground, as we said in our reasoning, right? That's F1, and then there will be twice tension upwards. I know this is a bit messy, but you guys get what I mean. So basically just drawing out all the forces, right? So we do force balance on top block, right? So we have, what are our forces? We have mg sine theta, mg sine theta, that equals to your F2 plus your T, right? So F2, or I'll first write T so that I can cancel it out later. So T plus F2. Now what's F2? F2 is equal to mu to N2. Now what's N2? N2 is mg cosine theta. So I'll say, instead of writing this, it's mu, sorry, mu to mg cosine theta. All right. Now, yeah, so T plus mu to mg cosine theta, and then bottom block, right? For bottom block, what do we have? We have pointing up the ramp would be 2t, right? So 2t equals to mg cosine mg sine theta. This is the component that points down the ramp. Mg sine theta, and then plus what? And then plus the two frictional forces, right? So mu2 mg cosine theta, and now the frictional force in the ground. And notice that our normal force is twice mg cosine theta, because we're looking at the bottom block, and experience is like, if you're just looking at the bottom block, it will experience a total normal force of 2 mg cosine theta. So plus mu 2 mu1 mg cosine theta. Okay? And now if we substitute what we got for t, right? And notice that we have mg and everything, so we can just cancel it out. So we have 2 sine theta minus 2 mu 2 cosine theta equals to sine theta plus mu 2 cosine theta plus 2 mu 1 cosine theta. All right. And then let's see. If I so there's a sine theta and 2 sine theta, and there's a negative 2 mu 2 cosine theta and a mu 2 cosine theta. So if I isolate sine theta terms on one side and cosine theta terms on another side, what I get is I get sine theta is equal to, if I factor out the cosine theta, it will look something like 2 mu 1 plus 3 mu 2 once you do the last one, right? So what do we get tan theta equals to 2 mu 1 plus 3 mu 2, and that's our final answer for theta. Some of you guys might have done, like, for example, 3 mu 2 minus 2 mu 1 instead of 3 mu 2 plus 2 mu 1, and that's because you messed up the direction of the friction force. So if you didn't catch it, so if you didn't catch our reasoning for the direction of the friction forces, make sure you review the recording. Just make sure, like, you need to relate the direction of the friction to the direction of the motion. Remember, if the friction force is pointed up the ramp, that means that the block is sliding down the ramp. And if the top block is sliding down the ramp, then the bottom block is sliding up the ramp, so the friction force between the bottom block and the ramp points down. Okay. We're pretty low on time, so let's just like go into the lesson. We only have like 20 minutes for it. So let's just quickly go through it. Kinematics, you guys should know all of this, right? It should be review your big 5 equations. Yeah. So let's go on to some more advanced kinematics. This should be a quick one. This is basically the idea is you want to use geometry when you're solving these kinematics problems, okay? So here's a problem from Kevin Joe. A boat can travel at a speed of 3 meters per second on still water. The boatman wants to cross a river while covering the shortest possible distance. In what direction should he row if the speed of the water is 2 meters per second? How about if it is 4 meters per second? Maybe I'll give you guys 1 minute to do some like quick thinking on this because we're pretty low on time. Take a minute, think about this. If you guys have any ideas, message me in the chat. So let's talk about it at when we get to the new hour, like 4 o'clock or yeah, 4 o'clock. We'll talk about it. Okay.
In which direction is the flow of the water?
You can in what direction is the flow of the water? Well, you can just assume, for example, if you have the river here, the water flows to the left. You can just choose any other direction.
And he's trying to get from the bottom line to the top line.
Yeah. You want to get from the for example, you're trying to get here to this shore over here, while covering the least possible distance. And remember, we're trying to minimize the distance traveled, not the time. Okay, if we want to minimize the time, it'll be a different story. Actually, it'll be the same. Wait, no, it's not going to be the same. So remember, here we're trying to minimize the distance traveled, not the time. Right, maybe. All right, let's go over it now because for time. All right, so first part, right? First part should be a bit more simple than the second part. Boat is traveling at 3 meters per second. The water is 2 meters per second, right? Um, like boat can travel 3 meters per second. This is on still water, okay? So let's first say you have a boat and it can travel 3 meters per second, right? Now we want to minimize the shortest possible, minimize the amount of distance traveled. What does this mean? Well, mathematically or geometrically, if we're starting at maybe this point over here, what we want to do is, for example, if the boat is traveling in this direction, and there's this angle over here, theta, we essentially want to minimize theta so that we cover the shortest possible distance. Because if you're just going from here to directly opposite of like wherever you are, you're of course minimizing the distance. If your velocity vector is pointing this direction, then the total distance you're traveling is going to be like from there all the way there, and that's obviously a really long distance. So we want to make the net velocity vector to be as direct as possible. Now in this case, part A isn't too bad because the boat travels at a speed that's faster than the speed of the water. So the water is traveling like its speed is down the river, right? So it's in this direction. Now if let's say the water goes in this direction, so for example, I'll draw over here. This is 2, right? How do I make it so that the net I want to make it so that the net, or like if I add the two velocity vectors, so the velocity vector of the boat if it was on still water and the velocity vector of the water, I want to add them together and make it so that it's perfectly vertical, right? And how does that happen? That happens if like this is 3, right? And this is 2. So I'm basically just forming a right triangle, right? This has magnitude 3, this has magnitude 2. In what direction should you row? You'll be rowing. Remember, this one will be the direction he's rowing. So it will be an angle theta, where theta is equal to cosine -1 of cosine -1 Right. Uh, the should be cosine -1 over 3, I think. Cosine. Yeah. Right. Yeah, you should be getting. Oh yeah, we're defining theta with this angle, right? So we're getting theta equals cosine -1. This will be 2, this will be 3, right? So cosine -1 2 over 2. That's your answer for part A, right? That's not too bad because the speed of the boat is faster than the speed of the water, right? Now, if you want to solve part B, it's a bit harder. So let's say we want to solve B using the same method we used in like solving part A, right? Will lead us to a bit of trouble because, for example, we want to draw that right triangle. Remember, before we had 3, 2, right? That formed the right triangle, and the net velocity was pointing exactly directly across the river. But is that still possible now? Well, for example, if I row in this direction, speed 3, a vector that's length 4, it will always cause it to point in that direction, right? And even if I went at the maximum possible angle, if I try to row directly to the right at with a magnitude of 3, right? So 3 meters per second, the water will still pull me to the left at 4 meters per second, and so the net velocity will be 1 meter per second directly to the left. I won't even be able to go across the river because I'm rowing towards the left. I'm rowing down the river and not across the river. So how would I do this, right? Well, here is where geometry comes into play, right? I can choose whatever direction I can row, right? So if I'm starting here, if I draw a circle, right, has radius 3, that'll show like any radius of the circle will be a possible velocity vector that I'm rowing. So I can row this direction, and then if I row in that direction, then that means that I'm rowing at this angle theta, right? Now that's the direction I'm rowing, but I also have to superimpose the velocity of the water, right? So if I do head to tail, right? So this will be let me use a different color. So maybe blue, right? Blue for this vector, and also blue for this vector. This is the velocity vector for the water, right? Now this velocity vector for the water, it points directly to the left. And I want to, basically, if I do the net force vector, so I'm doing head to tail vector addition, right? This will be the net force vector. So it points from there to there, right? Now, what do we want to do? We want to essentially maximize this angle over there. And how do you do that? You'll find that if this line over here is tangent to the circle, so essentially if this is theta, if that's angle is 90 degrees, then I'm able to maximize this angle over here. Now, if that's true, then it's pretty simple, right? So this is 3, this is 4, then this angle over here, um, right, that angle over here, so let's call this beta, right? Sine beta is equal to 3 over 4, right? So beta is equal to sine -1 of 3 over 4, but remember, that's not the direction we're rowing. That's going to be the direction of the final net force velocity, the final net velocity. If I want the direction we row, it should be this angle over here. This angle, which we'll call theta, we have cosine theta is equal to 3 over 4. So here we have theta equals to cosine -1 of 3 over 4, and that's our answer for part B. So basically, like if you want to, the takeaway from this is just we want to minimize the amount distance traveled, so we want to make the net velocity to be as directly down the as directly across the river as possible. In part B, it's a bit hard because we can't go directly down the river. So if we want to find the most direct way across the river, we have to use this geometry over here. And when you find that this velocity vector over here is exactly tangent to the circle we're drawing, then it's the most directly possible way, the most direct possible way cross the river. You can't do any better than that. He's a jump. All right. Let's see, what's next? Okay. Let's keep going because we're going low on time. So, all right, this one. Yeah, there's another kinemax problem I put in there, but and yeah, we can just skip it for now because I'll just give it to you guys for homework. All right, here's the idea. For fully problems, write out F equals ma equations for each mass. Be careful about tension forces. Relate accelerations of different masses using conservation of strength. Here's a problem over here. I don't know if we have enough time to do it, but let's see. How about before we do that problem, I'll talk you guys through linear momentum and energy, and if we still have time left over, we can talk about this problem, this fully problem over here. It should be pretty standard. Basically, the overall idea is you know the forces on each of them, and you know you have tension forces on each of them, right? Each of them it just experience gravity force downwards and tension force upwards. And now we want to relate the acceleration to these masses, right? So we know we're basically solving for like we know ma, let's say this is m1, this is m2, right? So ma1 equals to, let's say, for example, if this string has tension T1, right? That string tension T1, and this string will have tension 2T1, right? So ma equals 2T1, ma1 equals 2T1 minus mg, right? And then over here, because there are 3 total strings, right? So this will be T3, right? So ma2 equals to T3 minus mg. Now, how do I solve for A1 and A2? Well, I need to know T1 and T3, right? How do you find T1 and T3? Well, you're going to have to use conservation of string and figure out the forces on each of these pulley wheels, all right? I'll leave you guys do it for homework, or we might have time to do it. I doubt it, but the main idea is just you set up your F equals ma equations, and then you relate tension forces using conservation of string or whatever method like force balance on each pulley wheel. All right. Quickly go on to talk about linear momentum. Of course, we all know linear momentum E equals mv, mass times velocity. We have F equals ma, right? And because P equals mv, this is also equal to the derivative of linear momentum with respect to time, right? P over dt. Now, what does this mean? That means if you have no net force on the system, then that means your linear momentum is conserved because you have force equal net force, so sigma F is equal to dp dt. If your sigma force is equal to 0, then dp over dt is 0, obviously. And we can also say that when f external is equal to 0, then your linear momentum is conserved. Why? Because we always know that the sum of internal forces is equal to 0. Because internal forces, they come in action-reaction pairs. We all know this, right? It's from AP Physics 1. So if your F internal, we always know F internal is equal to 0. We can just say, if you have no external force on the system, your linear momentum is conserved. Also, if linear momentum is conserved in one frame, is conserved in another. We can give a quick proof of that right now. It's pretty simple. So if I'm going, for example, I have, let's say, the linear momentum in one frame. So P equals mv. And I want to translate this into linear momentum in a different frame. For example, P star, let's say P star, first vectors, right? Let's say P stars, say P star is moving at some, say, U star with respect to whatever frame we're in right now. Then that means that P star will be equal to M times V plus U star. And if I wanted to do the sum of all the linear momentum, the sigma P star is equal to sigma M times V plus U star, right? And if I did dP star over dt, right? Notice that because the U frame is inertial, right? U star is a constant. I always have du star over dt is equal to 0. So if now I do dp star over dt, then I'll still have it equal to 0 because we're given that d of p, we're given dp over dt is equal to 0. And because we're adding on a constant vector, u star, when we're taking the time derivative of u star, it's equal to 0 because it's just a constant vector. It's not going to change over time. So basically, we just proved that if your linear momentum is conserved in one inertial frame, so if the total linear momentum is not changing in one frame, then it's also not going to change if we're going in another inertial. Does that make sense? All right, hopefully it does. 2 minutes left, so quickly go on. All right, consider a system with many masses. I'll leave this to you for homework. Proof that in the center of mass frame, linear momentum equals to 0. It should be a very simple algebra, but yeah. All right, energy. Let's quickly just go over this derivation. It's very, very helpful for you guys, okay? Non-conservative, conservative versus conservative force. This will be a bit of calculus. So conservative force can cause a path-independent force. If you guys don't remember we have work. The definition of work is force, and then force vector, and then dot product with some displacement vector, some ds. For example, if we're looking at the work on the center of mass, it's just work center of mass equals to the integral of the force vector dot onto the displacement of the center of mass. And because we're doing dot product between two vectors, the work is always equal to a scalar, right? Now, what do we mean by conservative force? Conservative force, it causes, it's path independent, right? So it means that no matter what path we're doing this integral on, we're getting the same, we're just getting like, we're gonna always get the same amount of work. For example, if I have in space, my force is always pointing to the left. So, for example, at every point in space, my force points downward. So this will be sort of like a vector. If you guys learned this before, it's like a vector field, right? If I'm looking at the work done on a particle that moves from this point A to this point B over here, no matter which path it takes to move from A to B, it can go this way, it can go this way. It doesn't matter. It can also go maybe it'll go in this way in a very curly path. It doesn't matter what path it takes. It will always calculate the same amount of work. And for example, another way of saying this is just if we're looking at a particle and it moves, let me undo everything. Let's say it moves from point A back to point A. So it can take a path like that. It can take a path like that. It can just not move at all. If it takes a path that goes from one position and ends at another position at the same position, then what it means is just that there'll always be zero work done. That's just another way of saying it's a path independent force, like it causes a path independent work. So we call it a conservative force. Does that make sense? That's just our definition of what a conservative force is. Yeah, let's quickly go on. I'll give you guys a quick derivation of what energy is. This mindset is really helpful, especially when you're doing something like thermodynamics. It's helpful to keep this mindset in your mind, okay? So now, how do we derive like potential energy or like kinetic energy, right? So one way is to start from the work energy relationship, right? So we have work done on the center of mass is equal to the net work done on the center of mass is equal to change in the kinetic energy of center of mass. Now, what do we mean by work done on the center of mass or kinetic energy of the center of mass? Well, work done on the center of mass, that's just equal to integral of force dot onto the displacement vector of the center of mass. That's what we mean by work center of mass. Now, what do we mean by delta KE center of mass? Well, we just define it as equal to the change in 1/2 MVCM squared, right? That's just for MCM, what 1/2 of the total mass, because we're looking at the center of mass, right? So M total, and then V center of mass squared, right? We're looking at the change in this quantity, and the work done will be equal to the change in this quantity. Now, how do we go to potential energy, right? Now, work center of mass, we can divide it into the work done by conservative forces, work conservative, plus work done by non-conservative forces. And then this would equal to the change in kinetic energy of the center of mass. Now, if we move this to this side, right? The work done by non-conservative forces is equal to delta KE center of mass minus work done by conservative forces. Now, what we'll do now, this is where potential energy, where the definition comes, okay? We define potential energy such that negative work done by conservative forces is equal to potential change in potential energy equals the change in this quantity, right? The change in negative integral of F conservative dot onto BSCM. That's our definition of potential energy. And so what are we getting from this? Well, if you let's make a new page, and that'll just give us work done by non-conservative forces is equal to the change in kinetic energy from the center of mass plus the change in the potential energy of the center of mass. That's where we get potential energy from. And so if we want to look at our total result, by the way, for now, ignore this part. Let's focus on this part. Center of mass view of energy. The integral of force like this is just work done by non-conservative forces. We'll say change in kinetic energy on the center of mass minus this quantity, right? And we'll say this work done by non-conservative forces is a change in kinetic energy plus a change in potential energy. This is where we get, if you have, basically, how do we have energy conservation? We have energy conservation if all the work done is done by conservative forces. If your work done is done by conservative forces, then we can define potential energy of each conservative force. If you have no non-conservative forces, then your change in energy would be zero. That's what we mean by you have conservation of energy or conservation of mechanical energy. We're saying that there's no work done by a non-conservative force. So after this, I'll give you guys I'll give you guys a problem. Oh, something went wrong. So anyways, after this, I'll just give you guys for homework, there'll be a problem using this energy conservation idea. Yeah, I guess we went a bit over time today, but I think we covered all of the theoretical stuff. Now it's down to you to do a lot of the problem solving. That's the main part about getting better at physics, I guess. So, yeah, I hope you guys enjoyed today's class. It was a bit rushed. We did spend a lot of time on the homework, but I mean, I'm glad that we did because it's good that you guys understand, like everything that happened last week, and so make sure you guys review some of these slides. You guys in next week's class in 1 or 2 days, and please take a plan from it. And yeah, that's it. So you guys can have a good day now. I'll see you guys next week. Thank you.
Did you have a nice week?
Yeah, you too.
Thank you. Bye.
Thank you.
Thank you for everything.